right, so here's an example of a problem for LO3, for electric potential and capacitance. This learning objective focuses on capacitors and understanding how to simplify a series of capacitors into a single capacitor that's equivalent to the arrangement. Also being able to figure out how much charge is on each of the capacitors as well as the potential difference across them. We're also interested if you understand how to calculate the energy stored in a capacitor. So this particular example kind of does all those different things. Probably you wouldn't have as many things to do on your typical assessment, but I just thought this was a nice way to cover a lot of the material. So we want to recognize how our capacitors are connected. Capacitor 1 and 2 are in series with each other. Those two that are in series are in parallel with C3. And then that entire arrangement of capacitors 1, 2, and 3 is in series with capacitor 4. So we're going to carefully simplify this arrangement by taking each element and simplifying it until we end up with one single capacitor. The first thing I'm going to do is deal with these two capacitors that are in series and replace them by an equivalent capacitance. When I add capacitors in series, I add their reciprocals, and that gives me the reciprocal of the equivalent. And so if I do that, these numbers worked out pretty nice. It turns out that those two 4 microfarad capacitors that were in series are equivalent to a single 2 microfarad capacitor. So I'm going to redraw my picture. And what I did here is I actually drew it so it was more obvious that the capacitors connected in parallel to each other are actually in series with C4. The fact that it's around the corner doesn't really change anything. I can easily move this capacitor over here and it's the same situation. So this is where I am now. I've replaced C1 and C2 by a single capacitor. The next thing I'm going to do is I'm going to look at these two that are in parallel. And when I add those two in parallel, I just do 2 microfarads plus 2 microfarads equals 4 microfarads. When capacitors are in parallel, we simply add them together to find the equivalent. And so now I have 2 capacitors that are in series with each other. One has a capacitance of 8 microfarads and the other one has a capacitance of 4 microfarads. Finally, I'm going to add these two in series, so I add their reciprocals. And this is the first time my numbers didn't turn out pretty, but that's okay. I find that the overall capacitance of this arrangement is 2.67 microfarads. So this whole arrangement with a potential difference across them of 48 volts. And so this is from A to B. And a capacitance of, 2.67 microfarads. So 2.67 microfarads is the answer to part A. That is the equivalent of the entire arrangement of capacitors. If I wanted to find the energy stored in this arrangement, so I'm going to change the U total, is going to be, can be found by taking 1/2 the 2.67 times 10 to the minus 6 times the 48 squared. And what I was doing is I was using the expression 1/2 CV squared because I had all those values available to me. And that energy turned out to be 3.1 times 10 to the minus 3 joules. So that's my answer for part C, but we're going to come back and revisit this once I do part B, which is finding the charge and potential across each of the capacitors. So I found that the overall equivalent capacitance was 2.67 microfarads. I'm going to just remind us that our expression between charge, voltage, and capacitance is C is equal to Q over V. So I want to find the total charge that I have on this by taking the equivalent capacitance times the voltage. And I find that my total charge is 128 microcoulombs. That's going to be helpful for me because now I'm going to start working my way back. This is 128 microcoulombs is on this one equivalent capacitor. And now I'm going to start going backwards. Now, the 2.67 microfarad capacitor stood in the place of these two that were in series with each other. And I know that the charge of capacitors in series is the same. So both of these will have 128 microcoulombs of charge across them. Then I can also calculate the voltage across each one of those by rearranging this expression. My voltage can be found by taking my charge over my capacitance. And when I do that, I can actually find my potential difference across each of these capacitors. The 4 microfarad capacitor has a potential difference of 32 volts, and the 8 microfarad capacitor has a potential difference across it of 16 volts. Notice that if I add 32 plus 16, I get 48, which was the total potential difference across the entire arrangement, and that's what I expect. So that's good. I'm good. Now, if I go now back up to this expression, remember that the 4 microfarad capacitor was taking the place of these two that were in series. And so now I'm working my way back up. Now, the 8 microfarad capacitor, I'm all done with that. It has a potential difference of 16 volts and 128 microcoulombs. Now I have to think about the fact of these two that are in parallel. The 2 microfarad capacitors that were in parallel are have the same potential difference across them. So that's the rule that I'll use to go back from the 4 microfarad that stood in their place. So we found the 4 microfarad capacitor had a potential difference of 32 volts. So these will each have a potential difference of 32 volts. And from that, I can say Q can be written as C times V. So I can find the charge on each of these two capacitors that are in parallel to each other. And I find that they each end up having 64 microcoulombs. It's getting a little sketchy here. So I'm going to just write over here so where we can see it better. I found that this one had 64 microcoulombs and it had a potential difference of 32 volts. The 8 microfarad had a potential The 8 microfarad capacitor had a potential difference of 16 volts and a charge of 128 microcoulombs. Now, the 2 microfarad capacitor, let me try this. This 2 microfarad capacitor stood in the place of these two that are in series with each other. And because they're in series, they will have the same charge. So that means that both C1 and C2 have 64 microcoulombs across them. And the potential difference across each one of these I can find using this expression, and I find that C1 has a potential difference across it of 16 volts, and C2 has a potential difference of 16 volts. These two capacitors are going to be exactly the same because of the fact that they have the same capacitance. They end up with the same charge because they're in series, and also the same potential difference because we're working with the same numbers. So that's kind of a mess, but hopefully you can see it. I also wanted to find the total energy by finding the energy stored in each of the individual capacitors. Because what I wanted to show is that I could have found the total energy stored by looking at the energy stored on each capacitor and adding them all together, or I found the energy stored by looking at the equivalent capacitance and the total potential difference. So again, I'm going to use the expression of 1/2 CV squared, but I'll use them for each of these individual capacitors. So for U1, I have 1/2, 4 microfarads, and a potential difference of 16 volts. The potential energy across capacitor 2 is exactly the same. All the values are the same. The potential energy across capacitor 3 is going to be 1/2. It's 2 microfarads, and its potential difference was 32. And then finally, the potential difference across capacitor 4, it was a capacitance of 8 microfarads, and its potential difference was 16. And I want you to notice that when I add all these numbers together, I got 3.07 times 10 to the minus 3, which is basically 3.1 times 10 to the minus 3 joules, which is exactly the same as the value I got here using the equivalent capacitance. So I know it's a little messy, but hopefully you can follow it. There's also the example video you have on perusal for breaking down capacitors, but hopefully this helps you think about what kinds of problems you might see for learning objective number 3.